given by Holly Elliot from BGS on fertility indicators for carbonatite-hosted rare earth element deposits. Please go ahead.
Thank you. Lovely to meet you all. I'm going to be presenting some of the results that we had from the EU Horizon 2020 High-Tech Outcarb project. Finished a couple of years ago now, but I think it could be relevant to lots of the deposits that we have in Europe. So I'm not going to belabor this point. I really will be preaching to the choir as I say this, but we are transitioning to these new, cleaner technologies, net zero prospects, and it's going to require an awful lot of critical raw materials. So from the graph, we can see here that just comparing some of the more fundamental and more traditional types of energy production to our renewable energy, there is a huge amount more in terms of raw materials that we're going to need to produce these. And comparing one of our conventional cars, apologies, this laser is not very strong, conventional cars up here to the electric cars, again, a huge amount more raw materials are going to be required. And one of those, Eric will be happy to know, I'm going to be talking all about rare earth elements. So, what do we actually need rare earth elements for? Well, one of them, the major types, is technological advancement. So I'm talking things like computer chips, even medical equipment, but also things like superlight alloys, so very important for defense for each country. But one thing that's really been in the media a lot recently and is hugely driving the demand at the moment are our green technologies. So anything that is developed in order to help us reduce our carbon outputs. So that's things like our rechargeable batteries, electric cars, and also renewable energy. And that is really driving demand going forwards. So where do we actually find our rare earth elements? One of the major sources, and ones that we do have here in Europe, are our carbonatites. So for those of you not familiar, and for those of you who are, I do apologize, teaching you to suck eggs. Carbonatites are anything that is an igneous rock that contains over 50% carbonate minerals. So they're really weird and wonderful igneous rocks that instead of being silicate-based, are actually carbonate-based. Got some examples for you here on the screen from our fieldwork over in Malawi. So you can see very nice calcite crystals showing clear rhombic crystals. We've got some nice cleavage in there as well. But then we've got some things like this that look a bit dirtier, a little bit more rusty. So we've got an intrusion running through the ground here in Malawi. This is what it looks like to have something a little bit more iron rich and a little bit more manganese rich. But in terms of carbonatites, there's actually only one that is still active in the world today, and that is Aldenyai Lengai over in Tanzania. If you ever get the chance to look up YouTube videos for Aldenyai Lengai, I promise you won't be disappointed. These sort of beautiful, silvery, very low viscosity magmas coming out that are also incredibly low temperature. So when I'm talking about carbonatites, this is what I am talking about. But how do we actually explore for them? Well, actually, we've got a well-defined set of geophysical methods that have actually been published in terms of best practices by the High-Tech Outcarb project as well, if you are interested in that. Again, it's about a 400-page document, but that is available on the High-Tech Outcarb website. But one of the geophysical techniques we can use is magnetic surveys. And that is because carbonatites are chock-a-block full of magnetite. So they come up as really clear positive signatures on magnetic surveys. But as the carbonatites sit there cooling and crystallizing, they actually release oxidizing fluids out into the surrounding country rock. And that destroys any magnetite that might be in the surrounding country rock, converts it into hematite. So we get this sort of bullseye type effect in the magnetic surveys, where we get a really strong positive anomaly. I'm just going to give up on the laser, sorry. Really strong positive anomaly in the center there, and sort of a negative anomaly or a lower anomaly around the outside. And this is Sockley over in Finland. You can see that really clear bullseye type sort of pattern within the magnetic survey there. So that alteration around the outside from the fluids, that phenite, as I will come on to in a minute, creates a sort of negative anomaly around the outside. But we can also use gravitational surveys. Do have to be a little bit careful with these, because if we look at some of the average densities of carbonatite, it's around about 2.6 grams per centimetre. It's very similar to things like granite, which is quite often associated with carbonatites, and also can be very similar to metamorphic rocks. You can actually get a negative anomaly associated where it's intruding into a metamorphic rock. So this gravity survey you can see on the right-hand side there, that's actually from Mountain Pass over in the US. And I am going to have to point this out because I doubt you'll be able to see it from here. But this little tiny symbol in the middle there, that is the hammers, crossed hammers, that is Mountain Pass. And you can't really see any gravitational anomaly associated with it because it's carbonatites intruding directly into granites and metamorphic rocks. So we do have to be aware of that requirement for a distinction between the host rock and the actual carbonatite itself when it comes to using geophysical surveys. But we can also use radiometric surveys as well. As we've talked about, rare earths are incompatible elements, so the same geological processes that actually concentrate them also concentrate things like thorium and uranium. So we can use radiometric surveys to actually find rare earth-rich carbonatites as well. Monazite, often associated with these types of deposits, is quite high in thorium, so again, great for radiometric surveys. But also that alteration that we find around the outside of these carbonatites is quite potassium rich, close to the carbonatite itself. So again, we can find those through radiometric surveys. So again, brilliant exploration method. This map that you can see here is an example from Namibia. This is Lofdal, which is a heavy rare earth element deposit. And this is a thorium map that you can see here. So if you look at the actual high anomalies, you can see in pink, you can see that the fluids that are expelled from the carbonatite that are thorium rich are actually following some quite large regional trends and structures that are going through the area. So the fluids that are thorium rich are actually flowing along those lineaments. They're actually taking the rare earths out with them as well. So where we see this high thorium output, we also see these prospects of rare earth elements that you can see in yellow. We've already talked about hyperspectral surveys. They can be used to find carbonatites, but again, if you've got a very tricky, complex area, which it can be with all of that alteration, host rocks in there, it can be quite hard to utilize, but you can use hyperspectral imaging in order to find it. This is an example from Greenland. We've got the carbonatites in the blue, dark blue and light blue there. We've got the background country rock in the orange, and then the red is that alteration, that phenite around the outside. Now, coming back to this phenite term, it's very close to my heart. I spent 4 years working on it, so I will be talking about it a little bit more. So as the carbonatite's sitting there, it's cooling, it's crystallizing, it's releasing fluids out into the surrounding country rock. Now, as it's doing it, it is very rich in alkalis, and so as it is heading out into the country rock, it creates an alteration halo called a phenite around the outside. Now, that can extend up to 2 kilometers away from the source of the intrusion. So where you've got a carbonatite that is still undercover, like a lot of them are in Europe, this alteration is a really clear vectoring tool that we can use. Very similar to the porphyry copper type alterations, if you're familiar with the silicone model of porphyry copper. But not only that, but the phenites are also zoned. Very up close to the carbonatite itself, it tends to be potassic in nature. So around here in the middle, it's very potassic, may or may not be brecciated. Very clearly nice and pink because it's chock-a-block full of potassium feldspar in the outcrops. But as you go further and further away from the source, you head out into the sodic zone, which is characterized by these sort of green-blue sodic amphibole and pyroxene veins as you go further away. So that means that if we dropped a geologist out from a helicopter, lucky them, out in the middle of the sodic area, and they started heading towards the north, they'd head out of the sodic zone into unaltered country rock, heading in the wrong direction. But if they started heading in the other direction, they'd end up in the potassic zone, finally in the brecciated zone, and then closer to the carbonatite, which is hopefully going to host our nice, juicy, rare earth element deposits. Now that leads me in quite nicely to the fact that actually we got a well-established exploration method. We know where quite a few carbonatites are around the world. Alan Woolley, for those of you who know him at the Natural History Museum, actually spent his life's work documenting carbonatite and alkaline systems around the world. So as of 2008, when he actually published his database, there were 527 known occurrences of carbonatites around the world that have actually been nicely documented into an online database by the High Tech Outcar project that you can actually search. There is the website up there for you if you want to go have a look. The point that I'm trying to make is just because you have a carbonatite doesn't necessarily mean that you have a rare earth element deposit. And actually, if you go on this database, it's absolutely brilliant for geological information, but very little in the way of economic information associated with these entries. And so actually, in terms of mineralization, we know very little about some of these carbonatites around the world. So how do we tell which ones are rare earth element enriched? And there are clues that you can find associated with them, or fertility indicators, as I like to call them. One of them is the fact that rare earth elements are incompatible. That means that if you've got a long-lived, evolving system with lots of different magmatic phases associated with it, you are much more likely to get rare earth enrichment. So that means that as it's sat there, it's cooling, it's crystallizing, the rare earths are segregated into those late stage magmatic phases. That is where we're actually going to start getting more iron-rich carbonatites and therefore more rare earth-rich carbonatites. So actually, when it comes to fieldwork and trying to find these carbonatites which contain rare earths, we've got nice, clean calcite carbonatites on the left-hand side there, typically quite rare earth poor. You actually want the really dirty, scabby, sort of browny pink carbonatites on the right-hand side that tend to be quite sort of iron-rich, manganese-rich. So that's an example from Malawi again. Another example for you, rare earth poor, clean calcite carbonatite, nice, dirty pink and brown carbonatite on the right-hand side. Now, I'm not saying this is a rule, and there are exceptions to every rule, and those are typically associated with hydrothermal remobilization and late-stage rare earth enrichment that can actually enrich calcite carbonatites. There's always an exception to every rule. Here's an example of where that is taken into account, and again, Sockley over in Finland used as a case study. There are several different magmatic stages that we can see at Sockley. This is stage 1, nice big blue carbonatite in the center. It's a big calcite circular plug about 5 kilometers across, and it is a calcite carbonatite. There are areas in it that have undergone late stage hydrothermal alteration that has enriched it, but those are late stage alteration and remobilization. We've then got stage 2 around the outside, which is more dolomitic, so more sort of magnesium rich, and those are the radial and the ring dikes. And then stage 3, right down here in the southwest, those are the jammy dike complexes, much more iron rich, and again, much more rare earth rich down there in the southwest corner. So again, we can see that progressive set of magmatic stages and progressive evolution of the system towards a much more enriched rare earth end member at the end there. But coming back to my favorite phenites, those fluids that come out from the cooling and crystallizing carbonatite, they don't just phenitize the surrounding country rock, they also contain ligands. So we're talking negatively charged ions like fluorides, chlorides, carbonates. And what they do is they complex with or they surround the rare earth elements, and they actually greatly enhance their solubility within the aqueous fluids. And that means that the phenitizing fluids in the center coming out from the carbonatite will actually carry the rare earths out from the central source intrusion out into the surrounding phenite. And there they crystallize as micromineral assemblages, which are rare earth element enriched. And these are really easy to find within the phenite. So we're talking just standard SEM imagery. You can quite easily find these. Got an example on the left here. This is actually from Sockley. This is synchosite, so they're fluorocarbonates in the center there. So that is our synchosite. And then on the right-hand side over there, we've got monazite, which is from Mountain Pass over in the USA. So where we see these rare earth enriched micromineral assemblages, it suggests we've got a rare earth rich fluid and therefore a rare earth rich source intrusion that is coming out from. But these phenotizing fluids, they don't just form these micromineral assemblages, they also precipitate apatite within the surrounding phenite. I absolutely love apatite. It's like the dustbin of the geological world. So you get lots of different substitutions in there that actually allow you to show how the system is evolving over time. We can actually use cold cathodoluminescence images like these to actually image the apatite to determine the potential for rare earths within the system. So on the left-hand side, we've got two sets of apatites which show rare earth enrichment. At the top there, we've got sort of a green core, which is usually inherited from the country rock, surrounded by a rare earth rich purple luminescing rim. Or we typically have something that's a bit more homogeneous, like the blue-purple one from Mountain Pass down there. If we compare that to a rare earth pore system, we've got either completely unregimented zoning, like we can see down here, very different from crystal to crystal, even when they're sat right next to each other, or completely the reverse in terms of that zoning. So we can quite easily pick out the style of the zoning and the colors that are actually being shown up in that image in order to determine, do we have potential for rare earths within the system? But also the chemistry of those apatites can be used as a discrimination aspect as well. So we're plotting here yttrium against strontium, and the different colors that you can see are actually the zones that have been analyzed, the color they're luminescing within the apatite, and the different symbols that you can see are all of the different localities that have actually been analyzed. So we've got two control ones, which is Dorora and Tororo, and the rest have various different degrees of rare earth enrichment. And this is very sort of pilot stage. This is a very small amount of localities that we looked at. But what we can see is mostly the rare earth poor sit below the line, so actually low in terms of strontium and yttrium, whereas the rare earth rich sit above the line, much higher in terms of strontium and yttrium. And the last thing I'm going to say, because I don't want to keep you from your coffee too much longer, is the fact that some of these really highly enriched systems we see in rare earth elements actually have late-stage hydrothermal remobilization of rare earth elements. So where we've got very heavy rare earths, for example, we can actually get late-stage fluids that are ligand-rich come through the system and strip out either the light rare earths or the heavy rare earths. Now, those heavy rare earths, if they're stripped out, can be precipitated elsewhere when they might be concentrated, or they can strip out the light rare earth elements and leave behind the heavies. Obviously, the heavies are the more valuable, so that's what we want within the deposit. And we can actually find clues to this process going on within the phenite. So again, these are cold cathodoluminescence images of apatite. Sockly on the left-hand side here, very porous, very unhappy apatite crystal on the left. See lots of little holes in it, undergone hydrothermal remobilization. And then over in Malawi on the right-hand side, you can see that really fragmented core where we've had late-stage fluid come through and strip out some of the heavy rare earths that we can see there. So just to summarize for you, we are going to need more rare earth elements going forwards to meet that critical raw material demand. But just because we have a carbonatite, it doesn't mean that we have a rare earth element deposit. So actually, we need to actually determine the rare earth potential of a system quite early on before we have invested huge amounts of money in exploration drilling. Or if we have a carbonatite that sits underneath cover, we can actually develop some tools associated with that alteration, this phenite around the outside, that gives us clues that there might actually be rare earths present within the system itself. So, thank you very much.
Thank you, Holly. It's almost time for coffee, but I'm sure there will be some questions.
I think that's a resounding warm coffee.
Everybody's eager for. That's a question again from Torgel.
One question when it comes to phosphate and apatite. Could that be used as a, let's say, exploration tool to investigate.
For phosphates.
Yes.
So I guess because it's if the apatite is present, we can use it potentially as a way to determine whether there are rare earths. I have not looked into that. I've only looked at carbonatite sourced, but if the apatite is present, we can look at it through cold cathodoluminescence. Sorry, keep tripping over that. We should be able to determine whether there are rare earths actually within the apatite itself from that.
At least what I remember from Greenland is that some of the carbonatites there, they are associated with, let's say, unusual vegetation simply because of the phosphate.
Yeah, it's very true.
And so it could be so that one could make use of vegetation analysis to locate.
It's not been applied to it, but I completely agree it has potential.
Yes.
Any other questions? Down there.
Oh, thank you. In Eric's talk this morning, he spoke about Mount Weld and some other carbonatites which were enriched because of lateritic weathering. So what about transport or mobility of these rare earth elements in supergene environments?
So obviously they are fairly mobile, and it's one of the reasons that we have got quite a high level enrichment within them. I have no idea what effect that would have on things like the apatite potential. It's not something that we have looked at. Whether it would destroy that signal or not, I'm not aware. I have not looked at any lateritically weathered phenites associated with it. So apologies, I cannot answer that question. I'd rather be honest than try and say anything else.
Okay.
All right.
Well, thanks again. And then it's time for coffee